In this video, we are going to prove the rational root theorem. What is the rational root theorem? The rational root theorem is a nice little theorem that gives us some insights about rational roots of polynomials with integer coefficients. The theorem is not the most exciting, but has some cool consequences that we'll get into later in this video. The rational root theorem states that if we have a polynomial f with integer coefficients and our leading coefficient and constant coefficient are not equal to 0, if p over q is a rational root of f and the greatest common factor of p and q is 1, then p divides our constant and q divides our leading coefficient. For our proof, let f be a polynomial with integer coefficients. Suppose p over q is a rational root of f with the greatest common factor of p and q equaling 1. Since p over q is a rational root of f, we can plug p over q into f and get the following. Now we can move the exponents in. Now we can clear the denominators by multiplying both sides by q to the n. Simplifying down, we get this long expression of a n's, p to the n's, and q to the n's. And from here, we'll be able to set up two equations that will give us our result, one for our p and one for our q. For our p equation, we are going to take our a naught q to the n and subtract it over to the right side. This is going to leave all the terms on the left side of our equation with a factor of p, which we'll be able to factor out and have p times a ton of stuff equals negative a naught times q to the n. For our q equation, we are going to do the exact same thing. We are going to subtract over the an times p to the n term to the right side. This will leave all the terms on our left side with a factor of q. We will be able to factor out the q and get q times a giant mess of an, p to the n's, and q's equals negative an times p to the n. Simplifying both equations, we get one equation is p times an integer equals negative a naught times q to the n, and for the other equation, we get q times an integer equals negative an times p to the n. For our first equation, this means that p divides negative a naught times q to the n, and for our second equation, this means that q divides negative an times p to the n. Since the greatest common factor of p and q is 1, this means that p and q share no factors and are relatively prime with each other. Thus, we can conclude that p does not divide q to the n and q does not divide p to the n. Thus, we can conclude that p divides a naught and q divides an. Hey guys! I wanted to make a quick explanation of the relatively prime aspect of numbers. I feel like that aspect was a little glossed over, and you might be sitting there thinking, I kind of believe you, seems true enough, but I'm not 100% convinced. Just to try and convince you a little more, relatively prime numbers are numbers whose greatest common factor is 1. For example, 9 and 10 are relatively prime, since they share no common factors. 9 is 3 times 3, and 10 is 5 times 2, so they are both non-prime, but they can be treated as prime numbers relative to each other. If we are working on a problem and at the end we get something like 9 times p equals 10 times q, with p and q being integers, this means that 9 divides 10 times q and 10 divides 9 times p. Since 9 does not share any factors with 10, it means that n has to contain the factors of 9. We can then conclude that 9 divides q. We can use the exact same reasoning for 10 dividing 9 times p to get 10 divides p. On the other hand, if we have something like 10 times p equals 15 times q, we cannot conclude that 10 divides q since the factor 5 is shared with both 10 and 15. So we might lose that factor of 5 with 15. When the greatest common factor of p and q equals 1, p and q don't share any factors. When raising a number to the n power, we don't change the prime factors, just the power of those factors. So the greatest common factor of p and q to the n is also 1. Hopefully that added a little clarification. Now, back to the example. Here is a quick example of the rational root theorem. Let f be a polynomial equal to x to the n minus k, with n and k being natural numbers. The nth root of k is a root of f. Now let's suppose that the nth root of k is rational. By the rational root theorem, we know that p divides k and q divides 1. That means that the nth root of k equals p over q, which equals p over 1, which equals p. This happens to be an integer. Thus, the nth root of k, in this example, is an integer. This is a fact we will use in a moment. Now, let's suppose that there's an a in the naturals such that a to the n is less than k is less than a plus 1 to the n. With this, we could then conclude that a is less than the nth root of k, which is less than a plus 1. This means that the nth root of k is not an integer in this example. By part 1, the nth root of k had to be an integer, so we can conclude that in this example, k is not rational. Now we can combine these two statements together to form an overarching statement. We can now make the conclusion that for all k in the naturals, if k to the n is not equal to p, then the nth root of p is irrational. The proof is a combination of the two statements we just showed. There is a quick note that I should mention. Normally, we would have to show that there is an a such that a to the n is less than k is less than a plus 1 to the n, but I don't think it's too hard for us to believe that this is true. This is just saying that our number k is in between two squares or two cubes or two fourth powers. It's saying that if our k was 5, 5 is in between 4 and 9, or if our k was 10 and we are doing cubes, our k is in between 8 and 27. So I don't necessarily think that it's too hard to believe that our k is either something to the nth power or in between some number to the nth power and the next number to the nth power. So I think that it's perfectly reasonable for us to just accept this as true. It's not too hard to show that's true, but you'd have to dive into sets and do these things with some like infimums and supremums to show that this is the case, which is a lot of work for a very little insight. So that was everything. I hope you enjoyed. Thanks for watching.